In this quick tutorial, I'll show you how to use the intermediate value theorem. The theorem is perfectly summarized in this picture. And the idea behind it is that if you let f be a polynomial function where the input a is less than b, if you evaluate f at a and evaluate f at b, and they happen to have opposite signs, then there exists at least one real zero strictly between a and b. So pretend that that's f at a, the output, and the output of f at b is up here. Between f at a and f at b, given that they're opposite signs, there must be something in between where the root exists. So the question reads, find the real zero of f of x is equal to x to the power of 3 plus x minus 1, correct to 2 decimal places. Notice that in the question, they're not asking for the actual real zero. They just want an estimate that is up to 2 decimal places. To tackle this problem, I'll start by using Descartes' rule of signs, which tells us that if you see terms going from plus to minus or minus to plus, that will tell you how many positive real zeros there are. So notice that from x to the power of 3 to x to the power of 2, which is missing here because that has a coefficient of 0, there's no switch in symbols. And similarly, from x to the power of 2 to x, it's still positive all throughout. However, from x to the constant, there is a change that is positive to negative. So we can assume that there will be one real positive zero. If I were to substitute negative x into my function, I end up with negative x to the power of 3. That becomes negative x minus 1. All throughout these terms, there are no changes in sign. So there are no real negative zeros. Expect only one real positive zero. The reason why this is important for us is because now I can start to narrow it down. If I substitute 0 into x, where x is equal to 0, I end up with negative 1. So f at 0 is equal to negative 1. Now, given what I learned above about Descartes' rule of signs, I should test another number that is positive, because I'm expecting a positive 0. You see now why it was necessary to do that? So, if I substitute 1 into my function, 1 to the power of 3 is 1, plus 1, that's 2, minus 1 is 1. As you can see, between 0 and 1, there is a change in sign. At 0, it's negative 1, and at 1, it's positive 1. This means that something between 0 and 1 will be our root. Now that we've narrowed it down, and the fact that we know there will be one real positive 0, I'm going to select a random x value. Let's say that x value is 0.5. I just want to see where that will land. Using my calculator, 0.5 raised to the power of 3 plus 0.5, make sure that you substitute it into there, minus 1, and that gives me negative 0.375, negative 0.375. Now I know it needs to be positive, so that can't be my answer. Let's try 0.6. Now if I change these with 6, I end up with a less negative number, negative 0.184. Let's continue. Let's try 0.7. We're getting closer. Change that to 0.7 and this one. And this time we get a positive number, a positive output, 0.7, 0.043. So it has to be between 0.6 and 0.7 because of the change. Now I can't just take the average, of course. I need a number that is to 2 decimal places. You see, 0.6 and 0.7 were to 1 decimal place. Now, let's try 6.5. 6.5 is 0.07, negative 0.075, and the next one is 6.6. That doesn't work, so let's try 6.7. We need a positive output. Nope. 6.8. Not that either. Don't get frustrated. We try 6.9. And it works. So it is between 0.68 and 0.69. We conclude that the real 0 lies between x is equal to 0.68 and x is equal to 0.69. Therefore, the real 0 corrected 2 decimal places is x is equal to 0.68. If that's confusing to you, just think about it. If it's 0.69, it's past that point that we're looking for. So it has to be this, where that number right there, whatever it is, when rounding it, needs to be less than 5. That number needs to be less than 5. Greater than 5 would make 0.69, and that wouldn't work. So this is the answer to your port, and that is how to use the intermediate value theorem.